Welcome back. In the previous video, we motivated our study for dimensional analysis. Furthermore, we introduced the Buckingham pi theorem, which showed us a systematic way of reducing the parameter space of our problem by helping us to determine the number of dimensionless groups that are relevant. However, Buckingham pi does not tell us exactly how to form these dimensionless groups. It only tells us how many dimensionless groups we have in a given problem. So this leads us to the method of repeating variables. And this is a systematic way to help us identify the exact form of the pi terms in our problem. So the method is described as follows. So first, we need to list all the variables involved in the problem. And this can be sometimes difficult, right? It requires some intuition, maybe some expert knowledge, right? So in our example of the flow over a cylinder, we said that the drag force is dependent on the density, the viscosity, the diameter, and the velocity. Now, many times this can be relatively intuitive, but sometimes it requires some expert knowledge. Once we've listed all the variables involved, we need to express each variable in terms of the basic dimensions, which were introduced in the last video. So these basic or reference dimensions, or primary dimensions, there's several names for these, are mass, length, and time. We then use Buckingham pi theorem to determine the number of pi terms. Now the number of pi terms will be k minus r, where k is the number of variables in the problem, and r is the number of basic dimensions MLT that appear in those variables. Okay, so we determine the number of pi terms using the Buckingham pi theorem. Once we've determined the number of pi terms using Buckingham pi theorem, we select r repeating variables from step 1. Okay, so r is the number of basic dimensions that appear in our variables, and then we use that number r to select repeating variables. Now, what are these repeating variables? These r variables will be used together to non-dimensionalize the other remaining variables. Okay, so in our cylinder flow problem, we wanted to non-dimensionalize, let's say, the drag force. And so we would use some of the other variables, such as density, viscosity, to non-dimensionalize the drag force. Okay, so in this method here, we're using r variables together to non-dimensionalize the remaining variables. These r variables, so there's certain constraints on the selection of these r variables. And one of these is that these r variables must contain all the reference dimensions in the problem. So again, if we've noticed that we have MLNT dimensions that appear in our list of variables, then let's say we find that we have r is equal to 3, then the combination of these 3 variables must contain all the reference dimensions in the problem. Okay? And also, and perhaps this might be a bit intuitive, perhaps not, but we should not use one of the dependent variables, such as the drag on the cylinder, as one of the repeating variables. Okay? And then once we've done that, we form pi terms by multiplying the non-repeating variables by the product of the repeating variables, each raised to an exponent that will make the product dimensionless. So I'm showing this over here. Okay, so we have a non-repeating variable, ui, which will be multiplied by, let's say we have 3 repeating variables, u1, u2, u3. Each will be raised to an unknown power, a, b, and c. And we'll multiply all of these variables together and try to make them non-dimensional by finding what a, b, and c are. And then finally, we're going to express the relationship between the pi terms. Now, this is a lot to take in, but it's actually quite straightforward. And this method is best understood by an example. Okay, so let's consider a pipe flow. Okay, so we have a pipe over here, and it will have a certain velocity profile. Okay, and then another velocity profile further downstream. Okay, so our pipe flow, will have a certain flow rate, which we will call Q, and our pipe has a certain diameter, which we'll denote as D. And we're going to look at two stations along the pipe. And we're going to say that at point 1, we have a pressure 1, and at point 2, we have pressure 2. And point 1 and point 2 are separated by a distance L. So what we want to do is set up an experiment to determine the dependence of the pressure drop on the variables of importance in the flow. Okay, so we want to find the pressure drop, delta P, is equal to a function of something, right? So this is our experiment. So let's think through what flow parameters could affect the pressure drop along a pipe. Okay, so we can think that maybe viscosity would be important, the density, the diameter of the pipe, the length between the 2 points where we want to evaluate the pressure drop, the velocity, and maybe also our pipe has a certain surface roughness, which is denoted by epsilon. Okay, so with all of this, what we can say is that the pressure drop, delta P, is some function of the density, the viscosity, the diameter, the length, the velocity, and the surface roughness. So what do we have here? We have 1, 2, 3, 4, 5, 6, 7. So K is equal to 7 variables. Quite a big parameter space. Now, I'm not going to go through it in here, so you can check on your own, but all these 7 variables contain the basic dimensions M, L, and T. Okay, so the mass, the length, and the time appear somewhere in all these 7 variables. Okay, thus we can say that R is equal to 3. So M, L, and T are present. So Buckingham pi will tell us that we can reduce our problem to K minus R dimensionless groups. So that's 4 pi groups. So it will be something of the form pi 1 is equal to some function g of pi 2, pi 3, and pi 4. And we don't know what this functional relationship g is, and it doesn't matter. But what this tells us is which dimensionless parameters we have to vary. Okay, instead of considering all 7 original variables, we only need to consider the 4. All right, so we've listed all the variables involved in the problem. We've expressed each in terms of basic dimensions. We've determined the number of pi terms using Buckingham pi theorem. So now what we need to do is select our repeating variables. So r is equal to 3. Okay, so as mentioned, we don't want to select the pressure as a repeating variable. That's our dependent variable, so we don't want to select that. So, and again, these variables will help us to non-dimensionalize the other variables. So what we're going to do, we're going to select the density, the diameter, and the velocity as repeating variables. And we need to check that these contain all of the reference dimensions. So here we have m, l, and t that appear in the 7 variables together. So let's check. So we have the diameter, not the diameter, but the density is mass over length to the power of 3. The diameter has units of length. And the velocity, v, has dimensions of length over time. So we see that mass, length, and time appear. So we are good. So these 3 repeating variables are valid repeating variables to use in order to non-dimensionalize the remaining variables. Okay, so these remaining variables that we will need to non-dimensionalize are mu, the length, L, and the surface roughness, epsilon, and the pressure drop, delta P. Okay, so let's see how we're going to form our pi groups. So let's non-dimensionalize mu. So what we're going to do, we're going to say that pi 1 is the density mu multiplied by our repeating variables. So here we'll have the density rho raised to the power of a multiplied by the diameter raised to the power of b multiplied by the velocity raised to the power of c. And so now what we need to do is express each variable in terms of its primary dimensions. So for the dynamic viscosity mu, we have the mass multiplied by L to the negative 1 multiplied by time to the negative 1. So this is mu. Then we multiplied by the density, so the density is a mass multiplied by L to the negative 3. But now we're raising the density to the power a, so this will be to the power a and to the negative 3a. So this is our density. Next, we multiply by the diameter, which has dimensions of L, and we will raise it to the power b. Then finally, we multiply by the velocity, which has dimensions of length and time, and we're raising it to the power of c, So that's L to the C, T to the negative C. And what we want this entire product here to become non-dimensional. So what we want to equate this to the dimensions of mass raised to the power of 0, length to the power of 0, and time to the power of 0. Okay, so the product of these 4 variables, we want it to become dimensionless. We will have a dimensionless group if all of the dimensions is raised to the power of 0. And as you can imagine, equating the m, l, and t terms on the left and right-hand side will lead us to a system of linear equations. So let's look at this. So let's look at mass, for example. It appears in mu, so we have m to the power of 1. So let's just equate the exponents. So we have 1 plus a, which appears in the density here. We have a is equal to 0. Next, let's equate the dimensions of length on the left and the right hand side. So we have length appearing in the viscosity at the -1 power. So we have -1, and then -3a appearing in the density. Plus b appearing in the diameter, plus c appearing in the velocity, and this is equal to 0. And then finally we look at time. So we have -1 from the viscosity, and we have -c from the velocity, and this is equal to 0. So we solve this system of 3 equations and 3 unknowns. And what we will find is that a is equal to -1, b is equal to -1, and c is equal to -1. So what this tells us is that our product over here, pi 1, is equal to our viscosity divided by rho, v, and d. So this should probably look familiar. It actually looks really familiar to the Reynolds number, right? However, it seems to be inverted for some reason. And that's fine. So what we can do is that it doesn't change anything. We can actually just express this in its more conventional form of rho vd over mu, which is our Reynolds number. Okay, so we've solved for the first non-dimensional group, or pi group, by multiplying our non-repeating variable mu by our 3 repeating variables that we have selected as rho, d, and v, each raised to unknown powers a, b, and c. Okay. What are some of the other remaining variables? So we have pi 2, which we could look at. We can look at the length. So we can look at the length and non-dimensionalize it by multiplying it again by our repeating variables, rho to the a, d to the b, and v to the c. Now you can go through the same process as we did for pi 1, or you can save yourself some time and notice that all you need to non-dimensionalize the length, L, which has dimensions of length, is another length variable, which would be D. So we could say, without wasting any time, that pi 2 will just be L over D. But what I would encourage you to do is try this entire process out as we did for pi 1 by expressing this product for pi 2 in terms of the reference dimensions or primary dimensions, raise them to the power of a, b, and c, equate your dimensions m, l, and t on the left and right hand side, and find that a and c, which are the exponents for the density and the velocity, you'll find that these are equal to 0, and b will be equal to -1. We can do the same thing for our surface roughness. So our surface roughness, epsilon, has dimensions of L. So the surface roughness is a characteristic length scale that defines the material geometry at the micro scale on the surface. Okay? So again, we could do this whole thing where we multiply by rho to the A, D to the B, and V to the C, or we can save ourselves some time and just say that epsilon should be divided by D. So a length scale divided by another length scale would give us a non-dimensional group. But again, I would encourage you to, go through the entire process. It's good practice, and confirm that a and c, these exponents for rho and v, are 0. Okay, our last step is to non-dimensionalize the dependent variable delta p. Okay, so pi 4, we're going to look at non-dimensionalizing pressure by multiplying it by rho to the A, D to the B, and V to the C. All right. So primary reference dimensions for pressure are mass, length to the -1, and time to the -2. Right? Newtons per meter squared. You can check this for yourself. This is our delta P. We're going to multiply it by the density, L to the -3, and we're going to raise it to the power A, which is unknown. So that's density. Multiply by the diameter to the power B, which has dimensions of L. And then finally the velocity. So that's L to the C, T to the -c. Velocity. And we want to equate this to m to the power 0, L to the power 0, and t to the power of 0. We want to non-dimensionalize each primary dimension. So let's equate m, l, and t terms on the left and right hand side. So m appears to the power 1 in the pressure. It appears to the power of a in the density. And that is it. And that is equal to 0 on the right hand side. The length appears as -1 from the pressure, minus 3a in the density, plus b in the diameter, plus c in the velocity, and again we set it to 0. And then finally we look at the time, minus 2 from the pressure, and then minus c from the velocity, and we set it equal to 0. So we have 3 equations with 3 unknowns. So we find that a is equal to -1, b will be equal to 0, and c is equal to -2. Which tells us that pi 4, our dimensionless form of the pressure drop, is equal to delta p multiplied by the density to the -1, so that's 1 over the density, so we have rho, d to the power of 0, so the diameter to the power of 0, and the velocity squared. Now this should make sense, right? Recall from our study of Bernoulli's equation. Remember, Bernoulli's equation states that we have a static pressure plus a dynamic pressure plus a hydrostatic pressure, which is constant along a streamline. And look at our denominator here, rho v squared. It looks a lot like that static pressure. Not the the dynamic pressure that appears in Bernoulli's, right? It has dimensions of pressure. In fact, by convention, what we will do is multiply this by 1/2 as it appears in Bernoulli's equation. And this is just by convention. We would add this 1/2, okay? But this is not obvious from our method of repeating variables, and it's absolutely not necessary to add that 1/2. But I'm just showing this right now for completeness. So therefore, what we could do is we could express our results now in terms of a relationship between our pi terms, right? So we could do something like pi 4 is equal to some function of pi 1, pi 2, and pi 3. Okay, so our dimensionless pressure drop is a function of the non-dimensional surface roughness, the non-dimensional length between the 2 points between which we want to evaluate the pressure drop, and the Reynolds number. So the pressure drop is dependent on the Reynolds number, it's dependent on the surface roughness, and dependent on the length, and we can non-dimensionalize all of these so that our results are as widely applicable. So someone who is not running an experiment, but rather is just a practicing engineer, has a certain pipe, knows pipe flow, knows the Reynolds number, knows the surface roughness, knows the length between the 2 points, can evaluate the pressure drop by looking up results from a lab experiment and matching the Reynolds number, matching these non-dimensional lengths, and then solving for the dimensional pressure drop. And we will look at examples of how to equate these terms between, let's say, an experiment and something in a different environment. Okay, so in this video, we looked at the method of repeating variables, which is a systematic way of determining the form of our pi groups.